Greetings and welcome back. Today we'll be looking at the differentiation between bases and nucleophiles. That is to say, what sets bases and nucleophiles apart. We already know that bases and nucleophiles in general want to accomplish the same thing. So for instance, something like an O- is electron rich, it has too many electrons, and it would like to share them with someone else. We call it a base when it shares electrons with hydrogen, and we call it a nucleophile when it shares electrons with carbon or some other electrophile. So how can we tell the difference between a starting material that would prefer to be a base or would prefer to be a nucleophile? Let's start off with a specific example, which is this 4-carbon chain. It's a 2-chlorobutane, and I'm going to react it with sodium hydroxide. Well, we have two things that can possibly happen. If our hydroxide, remember that the sodium will do nothing, it's just a spectator ion. If the hydroxide directly attacks the carbon that has the chlorine attached, then we will form a new bond to that OH. This would be a substitution reaction because we would kick off the chlorine. We would end up with our hydrogen and that methyl group still attached there. And the right side of this molecule would remain exactly the same. So this is a substitution, and in this case we would say that that guy is acting like a nucleophile. Right, the other option is that anytime you have a leaving group attached to a carbon, that carbon is an electrophile. And we know that because the nucleophile just attached it. Attacked it. But the other thing that we have learned is that the CH right next to an electrophile is acidic. And therefore, we have another route that we can follow, which is that OH- could also act like a base for the exact same reason. It's got too many electrons, it wants to share them. The electrons between that carbon and the hydrogen could become a pi bond and kick off the leaving group. And therefore, what we would form is an alkene. We'd form a new double bond in between those two carbons. We would still have our CH3 and our H attached on the right side, and we would still have our CH3 and our H attached on the left side. There's a lot of stereochemistry going on right here, which we will dive deeper into a little bit later in the next few weeks or so. But for now, what I want you to see is that OH right here on the right is acting like a base, and it's attacking a hydrogen or sharing its electrons with a hydrogen that is acidic. On the left side, we have a hydroxide ion that is acting like a nucleophile, and it is directly attacking the electrophile. Both of these give you a neutral product. Both of them give you a neutral oxygen. Both of them give you a very stable chloride anion. Therefore, how can we figure out which one will happen? Well, in the case of this reaction, you'll get both. There is no strong preference for one versus the other. And the reason for that is that OH- or sodium hydroxide is a strong nucleophile, and it's also a strong base. So the first factor that can really help us to sort out whether a molecule will be a nucleophile or a base is really all about looking at how this nucleophile attacks. In an SN2 reaction, which is what we're seeing here, a nucleophile attacks an electrophile and kicks off a leaving group all in one step. It involves both the concentration of the nucleophile and the concentration of the electrophile, which is why we previously in class figured this out as a second-order reaction. It's a nucleophilic substitution because a strong nucleophile is required. Requires a strong nuke. And that nucleophile always has to come in from the opposite side of the leaving group. The reason for that is that the hybridization of this carbon is sp3, so we can imagine that there is a big old sp3 orbital right here. And what's leaving is the chlorine is leaving from the top. The oxygen needs to make a new bond, so the oxygen actually needs to attack that little tiny baby lobe of the sp3 right there and basically pull it through so that it can make a bond down here in the product. So it's an sp3 turns into another sp3 by, again, essentially grabbing the backside of that hybrid orbital that's making the bond to the leaving group and pulling it through this way. And therefore, we say that this reaction always goes by a backside attack. If you think back to the beginning of this semester, we talked a lot about hybridization, and hybridization happened so that the electrons could spread out as far as they could in three-dimensional space. We talked about three-dimensional conformations, so we had anti and gauche, we had eclipsed and staggered, and again the rationale is that electrons wanted to spread out as far as they could in three-dimensional space. Well, if we consider what else is going on here, there's a whole lot of crowding around that little nub that the nucleophile has to attack. Therefore, for a nucleophile, what is helpful, I'll write this down here, for a nucleophile, it's really helpful if it can fit in there. And there's one thing that helps it fit, which is polarizability. Polarizability helps, and that essentially means the squishiness of the electron cloud. I know that squishiness isn't really a word that we use in science very much, but it helps to get to the point. And so one thing that helps is having something that's very squishy. One thing that really hurts is having something that's large and bulky, because a big bulky nucleophile would have a very hard time fitting into that little hole right there. And therefore, something that's big and bulky wouldn't really be able to fit in there. And so for a nucleophile, bulkiness hurts. And those are actually the two big trends that differentiate nucleophiles from bases. A base can share its electrons with a hydrogen, whether it's polarizable or not, whether it's bulky or not. Therefore, really, when we're trying to differentiate a nucleophile from a base, we need to look into whether it's a great nucleophile or whether it's a bad nucleophile compared to its basicity. So let's get into some specific examples. First off, let's compare charge. If you look at a neutral species versus a charged species wants to share its electrons much more than a neutral species. Therefore, this guy would be a stronger nucleophile. In fact, we would usually call this a strong nucleophile. And it would also be a strong base. A neutral species, such as an alcohol, has electrons that it could share in a pinch, but it really doesn't want to, because if it shared those things, it would become positively charged, which is not great, or not stable, I should say. So therefore, this guy is a weak nucleophile, and it's also a weak base. But what about the bulk around it? Well, let's draw out some examples of this. If we have something like a tert butoxide, that is to say, a tert butyl group attached to an O-. This is something that is extremely bulky, and this guy would have a really hard time fitting into that little tiny lobe on the back side of our leaving group, and therefore this guy would not be able to do SN2 substitution very well. So this would not be a very strong nucleophile at all. In fact, this would be a very weak or almost impossible nucleophile. But it's still an O-. Sharing hydrogens, or sharing electrons with hydrogens, is very easy. So this guy, because it's a negative charge, is still a strong base. This is a huge trend, bulkiness. All right, so what if we have something like this? This would just be butoxide, or N-butoxide. It's 4 carbons in a row followed by an O-. Well, there's not a lot of bulk around that oxygen. Therefore, this guy would have an easy time reaching in there and doing that backside attack on the backside of the sp3 that attaches the leaving group. Therefore, this guy would be perfectly fine to be a strong nucleophile. And once again, because it is a negatively charged oxygen, it would also be a strong base. So the take-home message here, which is a really important one, is that if you're trying to differentiate the two, something that can be a strong base, which would do elimination, but not substitution. So we will say that this does elimination, because elimination is something in which it acts like a base, but not substitution, which requires a nucleophile. OH minus, which is actually akin to this guy right here, is both a strong nucleophile and a strong base. So just like we saw on the previous slide, this guy would do elimination and substitution, because that guy acts like a nucleophile and it acts like a base. All right, so let's look at some other trends. Well, when we compare things like a C minus to an N minus to an O minus to an F minus, in all of these cases, we're looking at something that is more unstable on the left and therefore more reactive on the left. We would say that really all of these guys are strong nucleophiles and strong bases, but they would be stronger on the left. So I'm going to say that these guys are strong nucleophiles. And then of them, I would say that F minus is the weakest. And they're also very strong bases, because just like we have on the left side there, a negatively charged species is going to be very desirous of sharing its electrons. Then F minus would be the weakest. All right, so that doesn't really help us to differentiate them, because all of those guys are strong. If you added a C minus, it would want to act like a nucleophile and a base. Therefore, you would get a mixture of elimination and substitution products. All right, but what happens when we go down within a column? So let's compare our F minus to our Cl minus to our Br minus to our I minus. Well, the larger they become, the more stable they become. So when it comes to bases, they're less likely to act like a good base because the I minus is most stable. So this guy would be a weaker base. In fact, we would say that F minus is a weak base, and when we go down to the bottom, they're almost negligible. But this would continue effectively in this direction in terms of becoming weaker and weaker and weaker, because the bonds to hydrogen would become longer and less stable. These guys would become, they're more and more stable by themselves with a minus charge, and so they're done, they're good. None of these guys down here would be basic whatsoever. But when we look at nucleophiles, F minus is a relatively weak nucleophile. But as we go down in that column, what we find is that larger things become more polarizable. Their electron clouds become larger and squishier. I'm going to draw this one kind of weird. F minus is a very tiny, very rigid electron cloud. It has a hard time getting in there and making that bond to the little tiny lobe of the sp3. It has a hard time doing backside attack. Therefore, that guy is a very weak nucleophile. But the further down we go in that column, they become stronger nucleophiles. Therefore, we have two competing trends. Things that are bulky can be non-nucleophilic bases, and we have some examples. Bulky, non-nucleophilic strong bases. These are what you would want to use if you wanted to do elimination, but not substitution. The one that we already drew up there is a great one. It's potassium tert butoxide. Sometimes we write it as TBUOK. We have also TEA, which is triethylamine. And the finest of all of them is this guy, lithium diisopropylamide. This is a very negatively charged nitrogen and a very positively charged lithium. Oddly, lithium and nitrogen will make a covalent bond, but it's extremely polar. So that nitrogen right there has a lot of bulk around it, but it's almost negatively charged, so it is extremely strong. And this guy is LDA. So anytime you want to have something that is a strong base but not a strong nucleophile, this is always going to be your answer. Use one of those three. If you want to use something that is a strong nucleophile but not a strong base, you want to look at larger atoms, because the larger atoms have more polarizable electron clouds. So larger elements within a column. So for instance, Br minus is a good one, I minus is a good one, Cl minus is a good one. These guys are pretty good nucleophiles, especially Br minus and I minus, but they're not going to be bases in the least. So that's how we can differentiate bases from nucleophiles. The vast majority of nucleophiles and bases are both nucleophiles and bases. However, these two trends let us figure out stuff that will work for one reaction but not for the other. So let's go back to that starting material from the second slide and look at what we can do to just get SN2, which is that substitution and required a strong nucleophile, or to just get E2, which would just require something that is a strong base. Again, we saw that if we used sodium hydroxide, which acted like both, we would get both substitution and elimination. All right, so let's start with elimination. We have a set of very strong nucleophiles that are not, strong bases that are not going to be nucleophiles, and we could use any of them. In this case, we'll use that triethylamine, or TEA. This is going to be far too bulky to get in there and attack that carbon, and therefore it's not going to directly attack like a nucleophile. So the only thing it can do is act like a base. It can pull that hydrogen off here from that carbon right next to the electrophile. It can move the electrons down and kick off the leaving group. And that would give us a successful elimination reaction where we would have our product of elimination, which is an alkene, but we would not get any substitution, and therefore we would have a pure product that is all alkene. It is almost all elimination. And basically no substitution. This is great because usually we're setting out to make something, and we don't want to make multiple things at the same time. Otherwise we'll have to separate them out. We've been doing a lot of purification in lab, and really it's not very fun. It's kind of going to waste a lot of product, and we'd like to prefer just one or the other. We said that the nucleophiles we could use, they were not basic, were very large, usually halogens. So we could use something like this, which would not be basic, would only be a nucleophile, and we could attack and kick that guy off. I hope that you're noticing the problem with trying to do SN2 but not E2. We have kicked off a leaving group that was chlorine in this case, and we've replaced it with a nucleophile that is not basic, which is chlorine. So, from a basic science point of view, that is to say, the application of this is not so great, but we have come up with a way to do all substitution because that guy is a nucleophile and not a base, and no elimination because it is not a base. So that's nice in theory. But in practice, you can see that one neat thing has happened here, which is the fact that every time you have a backside attack, you end up having the nucleophile come in from the opposite side of the leaving group. And that's how SN2 always works. So you went from something that was 1, 2, 3 R to 1, 2, 3 S. So we inverted our stereo center. We will talk about the chirality of this and the stereochemistry of this later, but for now, this video hopefully showed you how we can pick out something that will be a strong base but a weak nucleophile, and some things that can be strong nucleophiles but weak bases. Thank you very much, and I will talk to you soon.